Hello. It's very nice to be speaking at clojureD or at Complexity Conference, as it might be called as well. I work for a company called Pitch, but that's not what I'm going to talk about today. I'm kind of speaking to you in a dual capacity today, as a programmer and also as a philosopher. There's a time-honored tradition at Clojure conferences to kind of sprinkle your talk with a little bit of philosophy here and there. And I'm also going to do that. In fact, I'm wondering about whether it makes sense to apply some of the methods from philosophy to programming. I got started thinking about this topic, about complexity and about decomposing problems, when I stumbled upon this book by John Ousterhout. Ousterhout is a professor at Stanford University, so he has an academic background, but he's also, a real hands-on coder, you could say. He's the author of the Tcl programming language. It's kind of in the same space as Python and Perl and Ruby, also from the same era. And he published this book about software design. And it's a real gem. I really recommend it. It contains a lot of wisdom about programming. It used to be only available as a dead tree edition. But I think as of 2 or 3 weeks ago, there's also an electronic version of it. So like I said, I'm a programmer now, but I used to be a philosopher. And here are a couple of my philosophical heroes. So from left to right, there's Ludwig Wittgenstein, Elizabeth Anscombe, Wilfrid Sellars, and Robert Brandom. But I'm not going to talk about any of those either. But everyone has their heroes, right? So when I heard that Ousterhout was publishing this book called A Philosophy of Software Design, I knew I had to buy it right away because it kind of combined these two interests. And I do think that the connection between these two topics is pretty interesting. But anyway, there's a fair warning here. I will engage in a little bit of philosophy about programming today. But I also will talk a little bit more practically later on in the talk. So here's a rough agenda of what I'm going to talk about. First of all, the philosophy bit. Then I will talk about large software projects and the specific problems that we encounter when we're working on them. And then I will talk a little bit about what we can do about complexity. So this is the first talk, the first part of the presentation. And I'm going to start out with a philosophical question. So here's a question for you. What does a programmer do? And I know what you're thinking. You're kind of thinking, what kind of question is that, right? Programmers write code, or they drink coffee, or they fix CI scripts, or they spend some quality time in hammocks, right? So all of that is true. But I don't think it's the essence of programming, right? It's something we do, but is that really what defines us being programmers? No, I don't think so. So these are philosophers. This is the school of Athens. And philosophers have been obsessed with definitions. So basically with questions of the type, what is X? What is justice? What is truth? What is love? And so on. And in fact, philosophers have been interested in this kind of question basically since the beginning of philosophy in Greece. So here's a group photo, this time in color photography, of the main protagonists. And actually, I can zoom in into the detail in the middle. So here you can see the guy who's pointing up to the heavens, to the realm of ideas. That's Plato. And to the right, you can see Aristotle. So let's start with Aristotle first. Aristotle held that to really understand what a thing is or what an activity is, you need to know the good that it is aiming at. And he really thought that. I can prove it to you. because these are the first lines in the Nicomachean Ethics, his most celebrated book. In fact, it's the book that he is holding in this painting in his hand. So I'm going to read this really short quote. He says, those are the first lines of the book, right? Every sort of expert knowledge and every inquiry, and similarly, every action and undertaking seems to seek some good. Because of that, people are right to affirm that the good is that which we all seek. But there appears to be a certain difference among ends. Some are activities, while others are products of some kind, over and above the activities themselves. This is also to show that ancient philosophy is not very scary. It's actually pretty readable, right? So what does he mean when he talks about that good that we seek? Well, he talks about definitions of different things and activities. So for example, a knife is something that cuts. It is designed to be an implement that you use to cut things. And that also means that if the knife doesn't cut well, like the knife in your mom's drawer in the kitchen, right? Then it's not a good knife. Similarly, a house is something that gives shelter. That's kind of part of the definition of a house. So if it doesn't give shelter well, if it doesn't protect you from the rain, it's not a good house. The same thing can be said about activities or about disciplines. So the shoemaker makes boots or he makes sandals. And again, the standards of quality associated with activity derive from the product. So if he makes boots that fall apart after a week or two, it's not a good shoemaker. Finally, a bridge builder makes bridges, obviously. But if he makes bridges that crumble into dust after a couple of years, then he's not doing a very good job of being a bridge builder. So we can derive from this the Aristotelian question, what is the inherent goal of programming? So in the paragraph that I just read, Aristotle says that there's that the inherent end of an activity, that which it seeks, is either a product or another activity. So for example, the inherent end of shoemaking is the shoe, is the product, right? But he also says that some other activities have other activities as their goals. And I think programming is like that. It's one of those activities that have other activities as their goals. So we can ask, what is the characteristic activity of programming? What is the defining characteristic of programming? So think about how you approach a programming task. So at the beginning of a programming assignment, you kind of start with a problem that you want to solve, and you want to enlist the computer to help you solve this problem. And sometimes it can feel a little bit like this guy. So Sisyphus is trying to carry the rock up the hill, and you know the story, it always ends up rolling back down, and he has to carry it up again. And it can sort of feel a little bit like that working as a programmer. You're kind of feeling that you're standing in front of a hill with an almost impossible task. And why is that so? I like this phrase that has been coined by Ted Nelson. The phrase is possiplexia. It's kind of a feeling, and it's the feeling of being overwhelmed by possibilities. So either you're freezing in the face of the possibilities, or you're kind of trying to grab them all at the same time, and you can't get hold of any of them at the same time. So with a programming task, it often feels so overwhelming because you're thinking of the task as an indivisible whole. It's really hard to know where to start with the problem. And that makes it seem intractable. So the root cause of this feeling is the complexity of the task, right? Complexity, that's one of the words that we like to talk about. So we haven't taken the time to break the problem down into subcomponents. So we know what we have to do when we're feeling like Sisyphus. We have to take the problem, decompose it into components. Then we have to solve each individual problem by itself, and then kind of put the pieces back together to solve the original problem. And because each individual problem is smaller, it's easier to make progress on it than on the whole. So that's kind of the claim that I'm going to make here, a little philosophical claim. So the characteristic activity of programming is decomposing problems into subproblems. Problem chopping. So the defining activity of programming is not drinking coffee or lying in hammocks, even though those are things that we do as programmers. These are things that we happen to do, but they're not essential to the task. What I think is essential is this kind of problem chopping activity. So that's my Aristotelian answer to the Aristotelian question about the essence of programming. So if that's true, if programming is a little bit like slicing a pie into pieces, then it's also true, like slicing a pie, you can do it in many ways. It's also true that a programming task can be kind of sliced up in multiple ways. There's always different ways of decomposing a computational problem, and they're not alike. They're not all the same. So remember the Aristotelian view that the characteristic activity of things, or the characteristic activity of disciplines or expert knowledges, is closely related to their standard of quality. Right? The knife is only good if it cuts well, and the house is only good if it really protects you from the rain. So that means that you can break down a problem into subcomponents more or less expertly. You can do a better job, or you can do a worse job at it. And to understand this phenomenon, we have to go back even a little bit further than Aristotle to Plato. So that's the guy on the left. Plato liked to think about ideas. So the way you chop up a problem makes a big difference. There are good ways to do it, and there are bad ways to do it. And this is not at all a new idea. And actually, we can see this in this Platonic dialogue. So here he has Socrates say, the problem is to be able to cut up each kind, or each idea, according to its species, along its natural joints, and to try not to splinter any part, as a bad butcher might do. So here Plato is talking not about programming, obviously, but about decomposing an idea into smaller ideas. And what he's saying is, you can do a good job at it, or you can do a bad job at it. Philosophers can analyze an idea well or badly. So he sees this activity as similar to the work of a butcher. So back in the day, and even today, the job of a butcher is to cut an animal, to dissect an animal into its different cuts. But in order to do that well, the butcher needs to take into account the species of an animal, right? And a chicken needs to be cut up in a different way than a pig or a cow, because the cuts are different for the different species. So a bad butcher kind of doesn't take account of this difference, makes a mess of it, and cuts across the natural divisions of the animal. And that ends up causing splinters of bones and kind of making a mess of the whole job. Whereas the good butcher cuts along the natural joints of the animal, and you end up with nice cuts. So you can cut up problems well or badly, just like a bad butcher can mess up a job, and a good butcher can cut up an animal well. But it's still an interesting question why this activity seems to be so particularly difficult for programmers. So why is it more difficult in programming than in other disciplines? Right? It's not the case that problem chopping is unique to programmers. All other kinds of disciplines also do the same thing. So for example, a bridge builder also chops up a problem. He has a project to finish, and I'm guessing that he sets some milestones and finishes the first part of the bridge and then works on the second part and so on. But I think there's a difference between programming and bridge building, and for that we need to take a look at another quotation. And this is not from ancient philosophy, but from the 1970s. So here's Fred Brooks, from whom we already heard earlier today in Ben's presentation. And here is explaining what makes programming fun. So he's saying, finally, there's the delight of working in such a tractable medium. Basically, the programming domain. The programmer, like the poet, works only slightly removed from pure thought stuff. He builds his castles in the air, from air, creating by exertion of the imagination. So he was speaking at the time in the 1970s when the computational capacity was very limited and memory was very limited. I think we heard in Ingo's presentation today that in that time he was working with 64 kilobytes of RAM and not a lot of time in the time-sharing system. So even at the time, even when the computational capacity was very limited, people were already aware of the fact that the possibilities for abstractions are almost endless. And of course, today with much faster processors and much more memory, that seems even more true than it was back then. I think Brooks's description captures particularly well what is exciting about programming, right? We can build our castles in the air almost without any restrictions. It feels like the only limitation that we run against is the boundaries of our imagination. Anything we can imagine, we can build. So programming is different from bridge building. When you're programming, you don't have to keep to the physical constraints of the concrete and the bridge and so on. We are free to build our abstractions any way we like. We don't have physical restrictions, and we can build our castles in the sky. So, in conclusion, for this first part, I think that problem chopping in programming is hard in a particular way, in a way it is not hard or not as hard in other disciplines. And that's because we have many degrees of freedom, and we can build abstractions. We can build abstractions on top of abstractions, and we can climb the ladder of abstraction even more. And that's why I think that problem chopping by creating abstractions and modularization and so on, that's what defines the activity of programming. Okay, so let's get a little bit more practical. Let's talk about large software projects. And before we do that, let's talk about small software projects. So this is something I really like. It's the Advent of Code series of puzzles. It gets published every year around Christmas time by a guy called Eric Wastel. And it's just a small description of a problem about elves and Santa Claus and so on. And you get a little bit of input data that you can feed to your program. So you're asked to build a little program to complete a computational task. And you can pick any language that you like. And people do pick any language that they like. You know, there's everything from Python to Haskell in here. And in fact, there's also solutions in SQL and APL and everything in between. So what is difficult about Advent of Code puzzles? I really enjoy working on those puzzles, and I'm going to try to explain why I like it so much. So I do run into a snag every once in a while. It takes me longer than usual to complete one of the puzzles. And you know, sometimes that's because I'm fighting Clojure, because I forgot why we need type hints again and how they work, and you know, how do you deal with Java collections and stuff like this. But that's a negligible part of the problem. Of course, there's typos, but we can find the typos, right? That's off by 1 error, and it takes a little bit of time to debug, but that's not what hurts. What is really painful is the problem of misunderstanding the actual puzzle. And that's what really takes a long time. And that's not because the puzzles are not well designed, they're actually very carefully designed to avoid misunderstandings. And nonetheless, I sometimes got the task wrong, didn't grok it correctly. So when you misunderstand understand the problem, then it can take a painfully long time to get unstuck. So here's a scientific diagram that explains exactly, scientifically measured the distribution of accidental and essential complexity when working on a advent of code puzzle. So my guess here is that it's kind of like 80% essential complexity. And that's a very high number. That's only when you kind of find a nice solution to the problem. So we already heard about essential and accidental complexity in Ben's talk, so I'm just going to briefly read out that the definition in Moseley and Marx's Out of the Tar Pit paper. So what they write is, essential complexity is inherent in and the essence of the problem as seen by the users. And the as seen by the users is crucial here. And then accidental complexity is all the rest. Complexity with which the development team would not have to deal in the ideal world. For example, complexities arising from performance issues and from suboptimal language and infrastructure. So the fact that the essential complexity percentage is high in advent of code puzzles speaks to the fact that they are very well presented and you don't run into any of those incidental problems, or relatively rarely. That's, to me, part of why it's fun. So let's move on to large commercial projects. So there's a couple of differences here, right? For example, you get paid to work on a commercial project. You don't get paid for an advent of code puzzle. Except, if somebody in the room gets paid for those puzzles, then please talk to me after. Of course, there's many differences between a commercial product and a puzzle, a toy puzzle. But I think it's fair to say that one difference is that the essential complexity, the actual user requirements that we want to solve, is, the surface area there is bigger in a commercial product. Right? There's many things that the user wants, many requirements, which is kind of a good thing. That's what brings value to the business. But there's also a lot of other stuff going on. In fact, there's a lot of stuff going on at the same time, and there's a lot of moving pieces and interactions and dependencies all over the place. So here's my very scientific diagram about commercial project, and I think oftentimes the ratio is completely reversed when you're working on those projects. You can spend a lot of time on those accidental parts of the problem. Speaking about scientific diagrams, so on the x-axis you can see the size of the project. On the left-hand side there would be AOC, advent of code, and on the right-hand side there's like a long-standing enterprise application. And let's be generous and say that the essential complexity is rising linearly with the project time. But what is frustrating about these kinds of projects is that the accidental complexity is growing along with essential complexity, but it's growing faster than linear. It's growing in a hyperlinear way, at least if you're not careful. Yeah, and we all, or most of us probably know the symptoms of this disease. Something that was supposed to be a quick fix turns into this hour-long debugging nightmare. Something so that should be simple turns out to be actually really difficult to achieve. If you do a bug fix, it turns out to actually surface 3 other bugs in the process. And we kind of we keep tripping over our own shoelaces, it feels like. It's not a very pleasant experience. So if that happens, accidental complexity is becoming completely unmanageable. And I'm not saying this is something that has to happen, but it happens quite often. It feels like a dinosaur is kind of collapsing under its own weight. And if you're not taking countermeasures, if you're not mindful about this, then the collapse is not just a possibility, it's an inevitability. So remember this slide from early on, where I said that the only limits that we run against are the limits of our imagination. And yes, in theory, it's true that we can build our castles in the sky whichever way we want, but in practice, there is a fundamental limit. And the fundamental limit here is our cognitive capacity. It's our ability to understand the different parts that are working together. And even with a simple toy puzzle, it's already almost impossible to fit the whole problem into your head. And of course, it's much worse for a large project. So the thing that we need to optimize for is this scarcest resource. We need to be thinking about complexity basically all the time. For every change we introduce to the project, we need to think about how this change will affect the complexity account balance of the project. Will it make it more complex, or will it even simplify things? Or if you are thinking about a possible implementation of a feature, compare different designs and think about how these different designs compare as to their complexity footprint. This leads us to part 3. That's maybe the interesting thing. What can we do about it? How do we keep complexity from spiraling out of control? So of course, this is a Clojure conference, so we should be talking about Clojure. And of course, simplicity is one of the primary design goals of Clojure. From the beginning of the project, that was kind of baked in. And there are many ideas around that help us avoid complexity traps. So avoiding complexity is super easy in Clojure. Or is it? No, of course it's not true, right? Accidental complexity, avoiding accidental complexity is still not easy, even in Clojure. It is true that Clojure can help in a lot of ways. Clojure has features that help when it comes to keeping complexity in check. So for example, the focus on values, the focus on immutable collections, those really help simplifying things. And the same thing goes for many other features like concurrency primitives. So Clojure does get out of your way. It really tries to emphasize the practices that shield you from kind of unintentionally running into external accidental complexity. And as a community, we really care about simplicity, which is kind of evidenced by the fact that this is not the first talk at this conference about the topic. But there's a limit to how much the language can help. There's still infinitely many ways for your code to kind of turn itself into a tangled mess. And if we're honest about it, much of the accidental complexity that we have to deal with is really homemade. It's something that we can't really blame our tools for, something that we can't really blame our languages for. There's really no quick fix for the complexity blues. So 3 things that we can do, and I'm going to quickly talk about them in turn. First one is, of course, the best thing you can do is simplify your design. And I can't tell you a recipe how to do that. That's something that you need to decide on a case-by-case basis. Do check out Ousterhout's book. It's really great, and it has a useful taxonomy of all the different causes of complexity and some really helpful practical guidelines to help you make decisions. What I really think is a killer feature in Clojure are those 2 macros, namespace and function. And I'm not even kidding, right? Functions are the main instrument that we have in our toolbox for introducing abstraction. It's the most versatile instrument that we have. And similarly, a namespace is the most useful tool that we have for grouping functions into groups. And just using those two gets you a long way. Of course, on the internet, there's a lot of advice about functions. So for example, take this one. The maximum function length should be 25 lines, right? And there's projects out there that have a linting rule that rejects functions that are longer than that. Is that good advice? No, it's not. I think the only good advice that you can give about functions is that you should think long and hard about the interface that you want to expose. So the real remedy here is, I think, modularization and conscious thought about interfaces. So the contrast pair that you want to think about at all times is the contrast pair of interface and implementation. The interface is the part that is public. It's the part that everybody knows about, both the consumers of the module know about and the authors of the module. And then there's the implementation, which is private in the sense that you don't have to know about it unless you're the author of the module. So is there a question there?
Yes. So what do you mean with interface? Do you mean the type signature or?
Yeah, so the interface consists of two parts. There's the formal interface, which can be the type signature in a language like Java. In Clojure, it's a lot more dynamic, obviously. And the other part is the informal part of the interface. It's basically what you need to know in order to be able to use that module. So that would include documentation and doc strings and stuff like this. So going back to this, the interface should remain stable at all times, whereas the implementation can change without making changes to the interface. So introducing interfaces is really about empathy for the consumer of the module. You're caring for the consumer by trying to reduce the cognitive load that they incur when they're using the module. It doesn't have to be pure altruism, because it might very well be that the person who's using the module is you yourself in 2 years when you completely forgot about the implementation of this module. Or it could be in 2 weeks, as the case may be. Okay, so two main advantages of interfaces. Interfaces help with resilience to change, because you can keep the interface stable while changing the implementation, and the rest of the team doesn't have to know about it. And interfaces help you hide complexity, and I think this is really key. In order to use the module, you don't have to know all the ins and outs of the module. You only need to know the interface. You need to know the type signature, yes, but also and also the doc strings and the documentation of the API, but that's it. And there's also the idea of multiple implementations, and I think that's kind of cool, but not as important as the other two parts. Okay, so wrapping up. In order to define an interface in Clojure, you have a couple of options. You can use the def and minus function to signal that this function should not be called by external consumers. Or you can have a convention in your code base that if you don't have a doc string, that's kind of a private function, you shouldn't be calling it. And if you do, that you're doing it at your own risk. You could have like an implementation namespace and a public namespace. Or you could use a dev protocol, but really which way you choose is not as substantial as the fact that you're thinking consciously about this division of these two things. What do you want to expose as an interface? I guess the not very helpful rule is as much as necessary, but as little as possible. You want to keep the API surface as small as possible, but you also don't want to run into the situation where a consumer cannot do something that they want to do because your interface is too small. And finally, there's the danger of false abstractions, where you're kind of pretending that the interface is simple by hiding some things. But really, you need to know those things about the module in order to be able to use the module safely. And often that has to do with thread safety or state or things like this. So beware of false abstractions. So in conclusion, circling back to the beginning of the talk, the essence of programming is decomposing problems, is cutting a problem into modules. And decomposition means building abstractions and splitting code into modules. That really helps you keep accidental complexity under control. You should think about where to draw the module boundaries. If there's multiple designs available, think about how they are different with respect to the module boundaries. You should think about what to exclude from the interface. If you can throw something out, that can have a very powerful effect. And think about Plato's butcher and try to cut those modules along the natural joints. Thanks.
Thank you, Paulus.
Am I offside?